time. Thanks. Let me just like quickly do this again. Hi guys, I'm Kabir. I'm going to be talking about succinct arguments over towers of binary fields. Nice. Let's just skip straight to it then. Okay, yeah, don't be shy to interrupt me with questions. So yeah, so let's start with the first section, why snarks matter to industry folk. And so suppose you have a program, P, and you have an input, I, and you want to know what the output of running the program on the input is. You generally have two options. You can run the program yourself, or you can ask a friend to run the program for you. Now, both of these are not ideal. In the first case, you are sure about the output, but you have to do the entire computation yourself, which is expensive. And in the second case, you don't have to do any work, which is great, but you have zero guarantee that your friend gave you the right answer or even did the work. So snarks kind of are a fascinating like point in this trade-off space, and they give you almost like a perfect best of both worlds. And basically what this is like you ask someone to run it for you and give you a snark proof that this output is correct. Pro is that this is close to free, like it approaches like 0% of the cost. And there's a great guarantee on output integrity. You can get like 99.289% accuracy. And basically like this person cannot convince you of a false statement. As you'll see, like I'm kind of not like actually giving you the definition of a snark is. That's twofold. One, I think most of you probably seen it before, and two, like it's not actually important for this talk. So in short, like snarks enable verifiable computation, which is particularly great when you have like asymmetric computational power, right? So maybe like a resource constrained verifier and a like very powerful prover. And the main use case today, unfortunately, if you're not a blockchain fan, is it's blockchains. And specifically it's scaling throughput. So if you look at like these layer one blockchains today, like Bitcoin or Ethereum, you can think about them as like a shared computer that the world has access to. And that's cool that everybody has the exact same computer, but how do you make that happen? How do you make everybody agree on the same state of the computer? Well, it's got to be a really slow computer, right? Because everybody has to know what the state of the computer is today. So you can think about like this shared computer as being like a resource constrained verifier. And at like every step, it needs to like validate that I don't know, Alice wanted to send 15 Ethereum coins to Bob. Unfortunately, the slow computer can only validate like 15 transactions per second. Just for like scale, Visa does like 70,000 transactions per second. So this is like not nearly fast enough to treat like Ethereum like a payment processor platform. But like instead of validating like an actual transaction, what if you validate like snark proofs? Right? You just like batch 10,000 transactions together into one snark proof, and you say, hey, all these 10,000 transactions are valid. And like you don't actually have to do the work of checking these digital signatures and whatnot.
Wait, so I noticed one thing.
Yeah.
You write, on the first line, you write 15 transactions per second.
Yeah.
And the second one, you write 10,000 transactions very quickly.
Yes, I was intentionally vague there. You did catch me. I'm vague obviously because like it really depends on which proof system you use, what security parameters you use, like.
But like, is it like, is state of the art sort of things like good enough in this sort
Oh
of
yeah,
sense?
state of the art is like very, very
Okay,
fast. Yeah.
Okay.
So for this, the like application here, you're not just like you're also storing the like database of the computer off of the blockchain as well.
Yeah, yeah. I mean, I don't want to get too much into like the innards of Ethereum, but basically like you have everybody has like a node, and sometimes it's like a full node where it stores basically everything. And sometimes it's like a light node, which is like only storing like recent history or recent changes.
So you verify that the transactions are all
all
correct, but there's
yeah.
some big node somewhere that actually you
Yeah.
have to like update 10,000.
Yes, yeah. There's some big node that actually does everything. It's impractical to assume that every single client of Ethereum is gonna have everything. That's like, yeah, just like an implementation detail about a specific blockchain though. Cool. Yeah. I mean, so this is just like the high level gist. I don't want to get too into the weeds. I just wanted to like sort of tell you where all of this money is coming from in industry. It's like these crypto VCs basically who care about this kind of a problem. And these scaling solutions are sometimes called like layer two blockchains or layer two scaling solutions.
So just like to follow up on
Yeah.
the same sort of just like a rough order of magnitude sort of thing. Like, you say like Visa does 70,000 transactions per second.
Yeah.
Like with state of the art SNARKs and stuff, like how far off is Ethereum from that? Like, can Ethereum do that?
Ethereum is very well, it's not actually Ethereum, it's like a
Okay,
a
sure.
blockchain that sits on top of Ethereum
Okay.
kind of. But yeah, they're very, very close to that.
Okay.
Like
So does this mean that transaction costs come down as well, or transactions costs still like in
oh
the
boy.
jump
Oh man.
realm of
I'm gonna punt on that question because that's like an extremely complicated question.
like
Like,
gas and all this stuff as
yeah.
well that
Let's talk
still
offline
very
because
far.
yeah, this is a very, very, very complicated question. So let's talk offline about that. I also am not going to like pretend like I'm an actual blockchain expert or anything. But I do have thoughts on that. Yeah, okay. So that's like where snarks get used. I didn't even talk about like zero knowledge proofs or anything like that. I just wanted to talk about literally like verifiable computation. Um, okay. So now I'm going to give a quick overview of how modern snarks are constructed. And with the exception of like a few notable examples like Growth 16, which maybe you've heard of, most snarks follow this construction where we basically combine a couple of key building blocks. And one's called an interactive oracle proof, one is like a commitment scheme, and one is a hash function. And so before we show you how to combine these building blocks, let's first like define what an IOP is. IOP, if you haven't seen it before, it's basically like a generalization of PCPs to many rounds. So the prover is, there's some implicit relation here, and the prover is sending like these oracles, pi1, pi2, pi-l, to the verifier, and the verifier is reading some stuff and then sending some messages back. And we say that this IOP, interactive oracle proof, is public coin if these messages that the verifier is sending back to the prover are just random, like uniformly randomly sampled from some sample space. Yeah, so this is basically just like an extension of PCPs if you've seen that sort of stuff before. And at the end, the verifier has to choose to accept or reject. One sec. I'm going to get my pointer out. Okay, great. Cool. Yeah, and then much like PCPs, we can replace like each of these like oracles with an appropriate commitment scheme. And then we can compile our IOP into like a interactive proof like so. So instead of sending pi1 over, we send like a commitment to pi1, and then the verifier asks for some queries in pi1, and then we send like the answers of those queries and like opening proofs. And then the verifier sends us its message. And we repeat. We send a commitment to pi-l. Verifier sends some queries to like could be any of pi1 to pi-l. And then we send the appropriate answers and opening proofs back to the verifier.
So again, though this is an optimization thing or what, but
yeah,
with a public coin proof, you don't really need to answer until the end, right? Like, is there benefits to answering before?
With a public coin proof, you don't need to answer till the end. Is
like there's no reason to read part of the proof to send your response if your response is just uniformly random.
Oh, you mean on the verifier side? Yeah. That's absolutely correct. Yeah.
Like, is there a benefit to providing answers and proofs intermediate, or just do it all at the very end?
No, you're absolutely right. Like the verifier in this case could totally just just send all of its messages randomly, and then at the end just only send like QL. Oh shoot. Yeah, your optimization's totally right. The only reason I wrote it like this is because like when you're doing the compilation and it's not a public coin IOP, then like this is like exactly how it gets compiled.
With public coin IOPs?
No, but it's an interesting like question in research, whether like public coin IOPs are actually necessary. There's like this paper by like Chiesa and all, where they talk about this thing called public query IOP, which is something in between like a public coin IOP and just a general IOP. And they like posit that it might be true that the transformation I'm about to show you is still secure, even if the IOP isn't public coin. So it's like a theory thing, but I don't think in practice anyone really cares
So the
about.
idea is maybe with this, like, instead of requiring the stronger requirement of public coin, you have something that's a little weaker.
Yes, yeah.
Maybe you would make things more efficient.
But yeah, potentially. I mean, like if you're allowed to do more things, then you might have a more efficient thing to do. Yeah, but in practice, like nobody cares about anything other than public coin IOPs usually. Any other questions about this? Yeah, to say like some maybe obvious things, like an IOP is good if it's like complete, knowledge sound, succinct, very few rounds, prover efficiency is good, verifier efficiency is like exactly what you'd expect are the things that we look for in a good IOP. But most surely like we want completeness and soundness. And again, like I'm not giving these definitions because I think it's like stuff that you guys have seen before and you probably have like a flavor in your head of what that means. Okay, so there's different types of IOPs, right? Like here I was kind of like bootstrapping off of your intuition that like these oracles are vectors and that like these are queries into like specific points in the vectors. So that's probably what you're used to with PCPs. But what actually gets used often in like SNARKs in the real world is we do polynomial IOPs. So instead of these like pi1 to pi l's being vectors, we can think about them as polynomials, either univariate polynomials or multilinear polynomials. And what we do is these commitments are no longer like vector commitments, but they're polynomial commitments. And these queries are no longer like, show me a specific point. It's like, open this polynomial at a specific like evaluation point. And so instead of using like a vector commitment scheme, we're using a polynomial commitment scheme. So now back to modern SNARK construction, the way it usually works is like when we fix once and for all some NP complete relation R. I'll tell you what this NP complete relation we choose is later. We construct a polynomial IOP for this relation R. And then we compile this information theoretic object into like a real world object and interactive proof with the appropriate like polynomial commitment scheme. When I say like appropriate, if your polynomials are univariate, you should be using a univariate polynomial commitment scheme. If your polynomials are multilinear, you should be using like a multilinear polynomial commitment scheme. And then what happens is like we have kind of two parts. The first part is like called a front end. And it reduces like whatever arbitrary computation that you're trying to prove to like an instance of this relation. And you have a backend, which now you have like an IOP for this relation. You have a polynomial commitment scheme. You turn it into an interactive proof, and then you use fiat Shamir with some like good hash function, I suppose, and you get a SNARK. And like there's this result that says like if this is good, like this is complete and sound, and this is complete and sound, and this is complete and sound. And like if your hash function was like a random oracle, I suppose, then this would also be complete and sound. Great. Any questions about that so far?
Just, I guess like I don't really feel like I have a great intuition behind. I mean, like I imagine everything here is in practice land and everything is informed by like what sort of optimizations you can do. But like, is there a baseline reason why I should expect that like doing this all in terms of a polynomial IOP and polynomial commitments, like that's naturally better than just thinking of them as vectors and vector commitments?
Yeah, there is going to be a reason. I'll give you the short answer now. And like I'm not going to claim to know as much theory as you guys, but like these low degree extension kind of ideas generally, like what is the point of them? Like what's the like we use error correcting codes, like Reed-Solomon codes or whatever, a lot in practice. And what's the point of them? The point of them isn't like for error correction always. The point is that if I have two messages that differ in just one bit, comparing the messages means I need to compare like the entire messages against each other But if I'm comparing the code words against each other and I have like a code with really good distance, then I can only check in a couple of places. And so the point of like using like polynomials generally here, as you'll see, like this will be made clearer later. Point of using polynomials generally is that like I can check polynomials at random points to test if they're equal to each other. And that's like a way better test for the verifier than having to test like if the messages were what I expected them to be. Or like it'll be made clearer, but basically what we're eventually going to do is we're going to kind of interpolate a polynomial from like a vector. And we really want like this vector to have like specific structures, but instead we can like check the something about the polynomial. Right? So that's like the high level of what's going to happen. Okay. Time for the fun part. We're going to talk about a little bit of like as minimal math as we can do for this talk. So first, like multilinear polynomial, in case you haven't seen it before, it's just a polynomial that's linear in every variable. So this first example is a multilinear. The second one is not because it's the individual degree of x0 is 2, which is bigger than 1. And here's an important fact. A multilinear polynomial on n variables can be uniquely specified by its evaluations on the n-dimensional Boolean hypercube, which is just a fancy way to say this domain, 0, 1 to the n. And here's like it written out, like if you're given a specific function that maps like from this domain to some field, then there actually exists a unique multilinear polynomial. This is my notation for like polynomial over f on these many variables with individual degree at most 1. There's a unique multilinear polynomial that agrees with this function at every single point in this domain. Okay. And I mean, maybe you guys have seen this before, but like you can sort of think of functions as having like also a one-to-one correspondence with vectors, right? Like indexed vectors. Okay, so the definition is we call this like f twiddle the multilinear extension of this f. So this again is a function, and this is a multilinear polynomial. And I'm going to use like this notation a lot where I put the twiddle when I mean the multilinear extension of something.
Was f essentially just the coefficients?
Yes, essentially. Yeah, I mean if you think about it in like a Lagrange basis, then f is essentially your Lagrange coefficients, if that makes sense. Like here in this example, we'll see, like suppose f had these evaluations, then we define our f twiddle like this. The first evaluation times this like Lagrange coefficient, Lagrange basis polynomial. And like so. And what are these like Lagrange basis polynomials look like? Well, they to say the complicated thing first, they're actually the multilinear extensions of an equality indicator function defined over the Boolean hypercube. To say that in English, it's literally just this. It's just like this polynomial that is guaranteed to be 1 if these guys are equal to these guys, and 0 otherwise when these guys are inside the hypercube. So, I mean, I can just define them like this. And if you've seen like Lagrange interpolation before, it's pretty much the exact idea that you expect. Like, I want this function to equal like a0, 0 when x0 and x1 are 0, 0. Yeah, and these terms all get canceled out, essentially. And so yeah, it's exactly what you expect it to be. It's just like Lagrange interpolation on multiple variables. So you can think about F's evaluations exactly as like the Lagrange coefficients for this multilinear. Is everyone with me? Okay, cool. And then like, how do I evaluate at a point outside of the hypercube? I can't just read off the value anymore. Well, I literally just evaluate this multilinear polynomial I defined up here. Right. So I take like linear combinations of the Lagrange coefficients and the evaluated Lagrange basis polynomials. Okay, and yeah, like I said to Ethan, why is the low degree extension useful? The short answer is it like it amplifies small differences in these vectors. Long answer, stay tuned. The second piece of machinery that I'm going to need is I'm going to need to tell you about towers of binary fields. And I'm going to need to motivate a little bit why we care about these objects. Okay, so first recall that all finite fields of the same size are going to be isomorphic, but we still care about like the exact specific field that we choose and its representation and the arithmetic on that field. Like this matters in practice. It actually affects efficiency a lot, depending on which like finite field you choose of a specific order. So let's talk about towers of binary. Yeah. Yeah, because of hardware, because of the algorithms, like I will hopefully convince you of that in the next couple minutes, hopefully. So like suppose first, like I'll tell you about like what a tower of binary fields looks like. It's like a sequence of fields where each field is like contained in the other. F2, F4, F16, blah, blah, blah. And yeah, I'm using this notation T iota to indicate like the field that's of size like 2 to the 2 to the iota. And notably, like T iota elements can be represented in 2 to the iota bits. Okay, so formally, what I do is I start with T0 is equal to just F2. I don't really have a choice for which F2 I'm using. Then T1, I take like this T0 and I adjoin this X0 element, and then I mod out by this irreducible polynomial of degree 2. And so now this is like a degree 2 extension of T0. And then I do the same thing for T2 with T1, etc. And just take my word for it, but each of these like polynomials that I have here are indeed irreducible, which means that these guys are indeed fields. And if they're fields and they have the right size, then, we're good. Okay. So it's like proven in 1987 by this guy named Wiedemann that this is indeed a tower and that each of these guys are irreducible. And Fan and Parr in 1997 showed like really good algorithms for how you can do efficient multiplication and inversion in this tower. And specifically, like multiplication takes time, like O of n to the log base 2 of 3, which you might recognize as like the Karatsuba exponent. And here n is like 2 to the iota, which is like the bit width. Okay. So now,
say in
yeah.
this tower, it's like for everything, for all fields or whatever constructed this way, this is the complexity.
Yeah, so if I wanted to multiply like a T3 element with a T3 element, it would take O of n to the 1.59, where n is 2 cubed. Yeah.
What are you measuring in that O?
Oh, that's that's a great question. Like bit operations.
Okay, any bit operation?
Yeah, just bit operations. Any bit operation. Yeah, so here is like our tower of binary fields. And the natural question you might ask is like, okay, why are we doing all of this? Why are we not doing like the classical approach, right? If I want like a field of size like 2 to the 128, I can always just like adjoin x to f2 and then mod out by some like irreducible polynomial of degree 128. And there's a couple of reasons why we want the tower of binary fields rather than this like one-shot big field. The first is that we want to support multiple data types or data widths in our arithmetization. What I mean by arithmetization will make sense a little bit later, but to give like a little bit of a preview, essentially the way these front ends work is like you have an arithmetic circuit, right? And this arithmetic circuit typically is defined over like one big prime field. So think like circuit set, like Boolean circuits, that's an arithmetic circuit over F2. But you could generalize like circuit satisfiability to arithmetic circuit satisfiability over like, I don't know, FP for some large prime P, say. But we want to be able to support multiple data types. Like maybe not every wire should be constrained to be an FP element. Maybe we want some of the wires to be able to like be specified as coming from a smaller subfield. And that's why we're using these towers. Another reason is like we'll actually at some point want to use Reed-Solomon codes with alphabets of an intermediate size, f2 to the 16. So it'd be nice to have some field in between f2 and f2 to the 128. And finally, like the reason we're using these towers really is the fact that like we want these intermediate fields to be efficient. And what does efficient mean? It should be efficiently packable. So we should be able to like assemble 16 f2 values into like one f2 to the 16 value. We want like efficient small by large multiplication. It's like a question you might ask is like, if I do like f2 to 16, like I'm going to start calling them 16-bit. 16-bit by 128-bit, is that multiplication faster than 128 by 128-bit? We'd hope so. And it should also be efficiently unpackable. So let's compare, like let's really dive in and compare. In the classical approach, you see 128 bits, and this like represents some f2 to the 128 element. And you can think about these bits as basically being the coefficients, the monomial coefficients for some degree 127 polynomial. Okay. Is this element here in the subfield f2 to the 64? Like you can't just look at the bits and tell me. You'd have to run some computation. Like specifically, you'd have to like run like keep applying the FRI-Binius automorphism over and over and over again and see like whether the orbit of that is like at most 2 to the 64 in size. Maybe there's a better way to do it, but there's clearly like no obvious way to just like look at this element and tell me like, does this actually live in the subfield f2 to the 64? In the tower approach, you can see 128 bits for some f2 to the 128 element, and these are still like the coefficients, the monomial coefficients now, but for a multilinear polynomial in 7 variables. And it looks like this, and I'm going to really zoom into this, right? So you guys can like sort of make out the pattern. But the pattern that I really want to like emphasize is that in the first 64 bits, or like the first 64 coordinates, x6 is turned off. And then the last 64 coordinates, x6 is turned on. So what I can tell is like the first 64 bits don't contribute to any monomial terms with x6 in them. And the last 64 bits all do, right? So an element, like a 128-bit element, is actually in this subfield if and only if the last 64 bits are all zeros. Is that clear? Okay. So like similarly, like we can pack two like 64-bit elements into one 128-bit element in the very, very natural way of like you literally just like put the first 64 bits and then you put the next 64 bits next to each other. Okay. And like generally like these looking back at these towers like this, the I plus kth tower is like a 2 to the k dimensional vector space over like the ith tower with these basis elements. Okay. Now to wrap this up, like, so how do we do like small by large multiplication? Well, I just told you that this bigger like field is actually a vector space over the smaller field. Well, you can basically do small by large multiplication with 2 to the k small by smalls. And this is good because remember, same size multiplication is super linear. So the cost of a 128 by 128 multiplication is this, which I can decompose into this, which is bigger than this. And this is 4 times the cost of a 32 by 32 multiplication, which is the same thing as the cost of a 128 by 32 multiplication. So, in fact, by like using these intermediate fields, I now have a more efficient way of doing a small field times a big field element. And this can be like really, really exploited, like used a lot in hardware using like SIMD, like arithmetic, vectorized instructions and stuff. But okay, so this was just like a brief like foray into like binary tower fields and like why we care about them. In summary, it's for the reasons aforementioned. Like we'll be able to support multiple data types, and like these intermediate fields are very efficient. We can like pack them together, We can sometimes think about like 64 bits as like a 64-bit element, or we can think about it as like 64 1-bit elements. It's nice to be able to like go back and forth between like how these things are represented mathematically without having to change the underlying bits at all. And that's really nice for efficiency. Is that clear to everyone? Okay. Yeah.
So I have one question so you're defining your towers to be doubly exponential in iota, but you're also saying things like F2 to the 64 and F2 to the 128, which are not.
Yeah, they are. 64 and 128 are both powers of 2, right?
But they're not doubly, or
2 to the 2 to the 6 and 2 to the 2 to the 7.
Sorry, never mind.
Yeah, no, that's a little bit weird, always. Yeah. Any other questions? Okay. Cool. So now I'm going to try giving you a bird's eye perspective of the Binius IOP. And before, I promised you I would tell you what NP complete relation we would choose. And so the NP complete relation is going to be, I don't want to formally define it because it's just like makes it harder to understand, but it's essentially this thing we'll call Planckish arithmetization. And the way it works is our instance is like some two-dimensional table, partially filled out, and there's some copy constraints, which indicates that like two cells must have the same value. That's like a constraint. And then there's also a gate polynomial, which has arity equal to the number of columns. And the constraint is that if I apply this gate polynomial to each row, I should get 0. And so a witness is a fully filled out table, agrees with the partial filling, copy constraints hold, and for each row, g of row is equal to 0. Gate constraints hold. You might look at this and say like, okay, what is this? Like, why is this NP complete? What is this like even saying? And we can reduce from like arithmetic circuit set, which is, as I mentioned, is like kind of even more NP hard than normal circuit set. Suppose we have like this arithmetic circuit, 7, 3x, 26. And basically, like to satisfy this, it's basically saying like find x such that 7 times 3 plus x is equal to 26. Okay, how can we like reduce this into like a Planckish arithmetization instance? The way we do that is like for each gate, we create a row. And we have like these 4 columns, left, right, output, and is multiplication. And then we put like these appropriate copy constraints because the output of the 0th gate is in fact the left wire into the first gate. Okay. And now if it's the case that I can fill out this table, right, such that the copy constraints hold, and that this polynomial here on the right evaluates to 0 for every single row, then I've satisfied this circuit. So what is this polynomial saying? Like if the bit is 1, then I want L times R minus O to be 0. And if the bit is 0, then I want L plus R minus O to be 0. Any questions on why this Planckish like relation is NP complete? So as you can see, yeah.
It's like a quadratic problem.
Oh yeah, yeah. 100%. And there's maybe you've seen like R1CS and stuff before, but which is like even more constrained. Yeah, like to say a thing like this is clearly powerful enough to capture like more than just straight line computation like that. Yeah, this is like a more general thing than arithmetic circuit set. We just showed in reduction. So yeah, so in practice, like most front ends turn like arbitrary computations into some FP arithmetic circuit for some large prime P, and then they kind of apply this generic reduction, with some optimizations, and this kind of sucks, right? And the reason this sucks is because every single cell is treated like an FP element, But actually in practice, what ends up happening is most columns are just full of ones and zeros. And so with Binius arithmetization and using these like intermediate fields, what we can actually do is we can choose a different t iota for every single column. And this is awesome for many reasons. One, choosing t iota for each column like is automatically giving you free range checks. Like it's, you don't even have to prove that these things are bits anymore. You just like, they're constrained already to be bits. But more so, the witness is smaller in memory, and as it turns out, like the bandwidth pressure between like sending things between different hardware modules is actually a really big bottleneck for SNARK proving. And eventually what we do is we commit to every single column, and this is a non-trivial fact, but committing to like 128 bits is going to be noticeably more efficient and smaller in size than committing to 128 like big field elements. Okay. So that's the like, we've shown you the front end of what Binius is going to look like, kind of. Now let's.
What's the benefit of this front end versus R1CS or something else?
So R1CS, like everything is defined over the same field, like same big field, which there's many reasons why that's bad.
Like you're saying there's not like an equivalent way to say like we can, I don't know, treat some of the elements differently.
As smaller. So actually, so there's two things. First, most people are using like prime fields, and prime fields notably have no subfields. And so they can't do anything like that. And second, the few proof systems that were doing binary fields before this weren't able to get over this problem, which we call like the embedding overhead, which is this idea of like having to take your small field element, like pretend like it's actually a big field element before you do arithmetic with it. So like the key like thing about this work is really being careful about not doing more work than is necessary ever. Yeah.
A lot of them are going to end up being ones and zeros.
Mhm.
Where does that distribution come from? So like how likely is that to be the case?
Yeah, that's a great question. I can't give you like a perfect mathematical reason for it. I can only give you like the hand wavy like practical reason why that ends up being the case. One thing I did not tell you, for instance, is that like I only showed you one constraint here, right? And like these columns here are called selector columns. Often you have like a lot of these selector columns which just like turn things on or off, and often they're like very small field elements. Even if they're not always ones and zeros, like you can imagine that they'd often be like bytes or like U16s. Another like motivation for trying to do like Binius like arithmetization as opposed to what we had before is that these are kind of like more aligned with the actual data types that your normal computer supports. A big problem with like SNARK design today, or prior to Binius, let's say, was that things that were efficient to write on your computer are not always efficient to do in a circuit, right? Like the instruction sets are different, the cost metrics are different. Very simple example of that is if you want to compare if like this number is bigger than this number, your computer does that like this. But in like circuit world, you have to decompose it to bits and do this like really annoying thing. Prove that those bits are in fact actually equal to this number, and then like, compare the bit strings, and that's a lot of operations. So like what this is really trying to do is like try and reduce the gap between like what is good computation on your computer and what is good computation like when you're SNARK proving it, right? Yeah. Okay, so I have to tell you how to do two things. I need to tell you how to prove gate constraints, and I need to tell you how to prove copy constraints. So gate constraints. Let's take a new example. Setting, I want to prove to you that the 10th Fibonacci number is in fact 34. One indexing, in case anybody's like checking me in their head right now. So the instance is this partially filled out table. And my gate constraints are that this number minus this number minus this number is always equal to 0. Okay, for each row, this should hold. My copy constraints are that these diagonals should be the same. you should think about this as like f of n plus 1, and f of n plus 2 in terms of like Fibonacci's. Cool. So yeah, gate constraints for each row, these two should sum to this, and copy constraints, these guys should all be the same. For now, let's only focus on the gate constraints. So this is my witness. I was able to fully compute Fibonacci. And the way I'm going to do this is kind of interesting. So imagine in your head that you have like this vector D off to the side, right? And it's actually equal to the evaluations of every single row. What we want is we want to check whether this vector is a vector of all zeros, right? So how is the verifier supposed to check whether this is all zeros unless you're like just sending the whole witness to the verifier and allowing them to compute by themselves? Well, this is where like we use like the power of commitments and low degree extensions. And the idea is that like if we could take the multilinear extension of this vector D and then evaluate it at a random point, right? Like this multilinear extension of D is the zero polynomial, if and only if all of these values are zero. And then we have like a very good like polynomial identity testing to see if a polynomial is zero. You just test it at a random point, right? So ideally what we kind of want to do is like, commit to the multilinear extension of D and then have the verifier choose a random opening point and then send them an opening proof that, hey, D twiddle at R is in fact equal to 0. And how do we do that? D doesn't exist like it exists in our head. But we do have A prime, and we have A prime prime. And the prover can in fact like commit to the multilinear extensions of each of these guys. And then to evaluate D at R, we just simply like evaluate A prime, and A prime prime twiddle at R, and then run the gate polynomial on it. And again, like, why is this actually, succinct? It's because of the polynomial commitment scheme being efficient. You can evaluate this by yourself if you had access to all of this, but like we don't want to do that. Okay, is that clear to everyone? Like what the idea is behind checking the gate constraints? Okay. Cool. So in definition, like there's this IOP called zero check, which is like an IOP for a specific claim that a multivariate evaluates to 0 over the hypercube. In this case, like our multivariate is H, and it's just equal to like G, which you can think of as like a composition polynomial of these three multilinears. And the prover is proving that V is 0 over the hypercube. Now, a common mistake I want to highlight is this is not the same thing as proving that H itself is the 0 polynomial, because H is not necessarily multilinear if G, say, is like has total degree like bigger than 1. However, like D twiddle is defined like this. And whenever you're looking at like an expression and I'm telling you that like this is a multilinear extension of that, the way to check it is like put some like Boolean values for x0, x1, x2 on the left-hand side and the right-hand side and see whether these two expressions are necessarily equal. Because again, if they agree on the hypercube and they're multilinear, then they are in fact the same multilinear polynomial. Okay, so yeah, this was sort of like a quick intro into like how we reduce like checking these gate constraints into zero check. Now I have like, I'm not trying to plug myself, but I have like a YouTube videos about zero check and like the zero check to sum check reduction, which like unravels this thread a lot further because there's a lot more to go. That's like on YouTube and you can check that out if you want to, but I don't want to unravel this thread anymore. Like we got to zero check and then now like we can black box start at zero check and go down from there. The reason like I chose not to do this is because I think many of you have probably seen something sum check before. Okay, so we have a way to prove gate constraints if we have a way to prove zero check. how about copy constraints? Well, Binius doesn't actually do copy constraints. We use these things called virtual multilinears, and roughly like a virtual multilinear is like a way to manipulate or reshape a committed multilinear in some useful way. And so we'll highlight two useful ways. Imagine we have like a raw committed column A here of bits. We can, in our heads, imagine like a column of like 64-bit elements of size like 64x fewer elements, just by like packing these guys together contiguously. This is going to be useful as you'll see. And notably, like if I want to evaluate this, like the multilinear extension of this packed column at some random point, there is a formula to do that. That's basically like a sum over 64 elements. Then there's also this like thing called a shift construction where I can take a raw committed column A, and in my head I can imagine that I actually also have access to like a virtual shifted column. And I can do these shifts kind of in all the ways you would hope to be able to do them. I can, do a circular rotation by 3 positions, say. I can do a rotation and I zero fill at the top. I can even do block-wise shifts where I chunk things up into blocks and then shift within my block. So, this is really giving someone who's trying to design a circuit all of the power to choose how they want to like arithmetize things. Yeah, and what I kind of really want to say is like this is also, you can evaluate the multilinear extension of this vector efficiently as well. And these like tools actually give you the ability to do things that are way more impressive than copy constraints. So shift, like in a nutshell, allows you to compare columns, but you don't have to commit to something new, which is really nice in terms of proof size and efficiency and whatnot. So you actually don't need copy constraints in the Fibonacci example. You can commit to A and let like A prime and A prime prime be like shifts of A. Okay, is everyone with me like in spirit? Okay, great. So there's a couple problems. First one's pedantic. The shift doesn't exactly work because like these guys are not shifted values of anything in A. Fine, we can modify our like input like this and do some like zero filling. Okay, that's like annoying, but we can do it. Then we can also add like this selector column B, which basically tells us whether we want to turn on the gate constraint or not. Like so. Okay, a little bit pedantic, but that fixes those small issues. There's a much bigger issue though. The subtraction is happening in a binary field, right? Like this whole time I've sort of been pulling a fast one on you and saying like, oh, we're just like saying that this value plus this value equals this value, and 3 plus 5 equals 8. Well, 3 plus 5 does not equal 8 in binary fields, unfortunately. Yeah.
Is like kind of pre-processing, right?
What do you mean?
It's kind of optimizing a little bit, like optimizing the data so that more compatible.
Oh, pre-processing is, I wouldn't like call it pre-processing. I would call it more like choosing your instance intelligently, if that makes sense. Do you like the prover and verifier get to agree on some instance beforehand, and both of them are like going to choose an instance that is like nicely designed for good proofs that does the thing you want it to do.
Okay.
Yeah. Yeah, so the second problem is like subtractions happening in binary fields, which is just like an XOR of bits, and that's no good. Okay, so how do we fix that? Well, all of you are excellent software engineers and know the importance of modularity. So we use gadgets. And there's many of these gadgets, and gadgets are an idea that gets used in SNARK design a lot. Yeah, basically we can create an addition gadget, and the upshot is that it's not that much overhead in order to be able to create an addition gadget. You pretend like you have these columns of bits, and then you can commit to C out, which is like the carry bits, and you can let C in be the shift of carry out. And essentially what you want is you want to constrain that like Z is always equal to X plus Y plus carry in, which like tells you the correctness of this value here. And the carry out is always equal to 1 if and only if 2 or more of X, Y, and C in are 1. Like, okay, this is like a complicated way to write it, but like really C out is equal to 1 if and only if at least 2 of X, Y, and C in are 1. Okay, and ta-da, we've arithmetized like addition of bits. Right. This is cool. Yeah, and then I have 2 constraints here. Multiple constraints is actually okay. You can always like batch together 2 constraints using like a random verifier challenge and do some like linear combination. As I said, there's smart ways to do what I just said, and there's worse ways, but just for now, just like assume that it's okay. We can have multiple constraints, multiple gate polynomials, essentially. So cool. We have just 2 constraints, a shift, and an extra column. Right, that's not too bad. So what does Fibonacci look like now? Looks like this, right? So we have A, we have C out, we have A prime, and C in. Now, the blues are the real committed columns. The reds are all virtual columns. And this is awesome because we get access to like all these virtual columns without having to do anything, right? Like they're just free. You don't have to commit. You can basically derive whatever you need to derive about them using the committed columns. Yeah, and like you basically do your gate constraints on this trace and that'll work out great. Theoretically, one could also put gate constraints on this trace. Like maybe you wanted some constraints about these values, except when they're like F2 to the 8 elements. So this really gives it like a lot of power to not have to ever do this decompose to bits operation that I mentioned is like really annoying in normal snarks. Cool. So yeah, so the truth is like I can't even begin to scratch the surface with like explaining how useful and important like intermediate fields are when trying to do arithmetization. Yeah.
Still a little bit separating in this example, the instance and the witness.
Sure, yeah.
The instance and what is the witness?
Right. So the instance is just like a partially filled out table, is how you can think about it. So in this case, everything I've highlighted is the instance. And then everything that's not highlighted is the part of the witness.
Problems with adjustments. You were mentioning the values that were not highlighted as being, oh, this is a problem. Like we have to, the shift doesn't quite work because these, like, right. So
Oh yeah.
Seems to be done partially based on the witness and partially based on the input. And I'm just wondering what does that look like between the prover and the verifier?
That's a good question. Yeah, that's a great question. Let me think about that for a second. That's actually a very good question because like a priori, why would the verifier? Okay, so I think this is how I would say it. The prover kind of knows what optimizations it would like to do. And it tells the verifier an instance, and the verifier should be able to like look at the instance and say, okay, this actually is an instance that does the computation that I care about, right? There's multiple instances that satisfy the verifier for a specific computation, right?
Doesn't anything about the input. Like if I'm the prover and for my specific input is giving the verifier the instance leaking information about my witness.
That's a great question. In practice, like yes, actually the circuit you choose is some leakage potentially. However, these are not ZK snarks. These are just snarks. So we don't care about like leakage. In fact, like ZK can be kind of annoying if you're trying to deal with all the timing attacks, especially when we've done all these like optimization stuff. Yeah, but these are just snarks. And okay, to say a thing like if you really want ZK, what you can always do is you can take a snark and then you can just recursively wrap it up in your favorite ZK snark, which is what most people do these days because recursion overhead has gotten so much smaller than it used to be in the last couple of years.
So how common is it to do all of these specific optimizations for Fibonacci versus just like I don't know, and like use a general circuit to describe what you're doing, like you're proving some hashes are correct or whatever.
Oh yeah, so proving hashes are correct is like actually the biggest thing that people care about in industry.
Because it seems like with something like that, you can't really do these clever optimizations, and you just kind of have to like encode it as a circuit.
Oh no, there are like there are better and worse ways to like prove that a Keccak hash is correct. And there are tons of optimizations there too.
I see. So I guess it depends, like in those cases, like which hash you're using.
Yeah, in fact, like the big overarching motivation for Binius in the first place was that most of these snarks were using like arithmetization friendly hash functions that nobody really trusts. Maybe you've heard of like Poseidon or something. And if you haven't, that's kind of the point that you haven't heard of it. And Binius, like my former bosses were like, this is nonsense, right? Like we should just figure out how to arithmetize like true and trust like already trusted hash functions properly and fast. And so now like with this kind of an arithmetization, you can actually do like Keccak proving really, really fast. Yeah.
Complexity of doing this optimization, I guess like on average, like is there some, because it depends on the instance and the witness size, right? It's like, what is the upfront cost of the prover having to optimize the circuit versus to like shrink the proof size versus like the traditional way?
So like optimizing the instance, is that what you're talking about?
Yeah.
That's like a problem that people call like the front end of proof systems. Like there's a lot of interesting work in how to take an arbitrary computation and turn it into like an optimal circuit. What I'm mostly focusing on is like the back end, like when you start with that instance, what do you do with it then? But the front end is like very much an interesting problem. I would say that my short answer to that of what's happening today is like most people are doing uniform computations. And there are these things called ZKVMs. Maybe you've heard of this buzzword before, which basically like proves a step of say like a RISC-V processor. And this is like a very uniform computation. So you fix once and for all like a circuit that's really good at proving that this step happened correctly. And then once you've done that, there's no more thinking front end wise. Cool. I don't know if I'll have time for this, but I will maybe give the world's like fastest. I don't know if I can do this justice in like a fast way, but maybe I'll like say some words which might resonate with you. But one of the really interesting parts about this work is the small field multilinear polynomial commitment scheme, right? And specifically, that's this idea that it's like more efficient to commit and open like to bits rather than to big elements. And the reason that many people before this were not using binary fields was this embedding overhead problem. Like I don't know how to commit to like a vector of or the multilinear polynomial over like F2, let's say. And the way that there have been multiple iterations since then. I'm giving like a very high level overview now because like I don't have too much time. It's first we did one that was like based off of Breakdown. Now there's one that's based off of like BaseFold, which is like a FRI-based polynomial commitment scheme. There are multiple different FRI-based polynomial commitment schemes. If you guys are familiar with FRI, don't know. Okay. It's like never mind. I'll tell you about it later maybe. But yeah, so the first one that we did was the simplest to understand, and it's based on Breakdown, and it's still not simple to understand, to be honest. I'll kind of try and give you like the super fast version of it. Essentially, the way you commit to a multilinear is you collate the evaluations of the multilinear over the hypercube into this like 2D table, m by m, and then you row-wise encode every single row using some like linear code that has good distance, like constant relative distance, let's say. Okay. And then to evaluate this multilinear at some point R in like f to the log n, what you'll do is you'll split R up into like a first half and a second half. And you'll let Q1 be like the expanded tensor of 1 minus Ri for the first half. and you'll let Q2 be like the expanded tensor of the second half. And what the prover does is it sends like this Q1 linear combination of the rows of U to the verifier. And it like, I'll write it here, like you get a Q1 linear combination and you get this like value U prime prime. And so this is sent to the verifier. The verifier will encode this guy and get, I don't know what I want to call it. Let's call it like U hat prime prime. And U hat prime prime should be a Q1 linear combination of like the rows of U hat, right? And you can imagine that the prover has like Merkle committed to the columns of U hat, let's say. Then the prover like opens like, so the verifier can now check whether this guy is in fact equal to a Q1 linear combination of this guy. But it doesn't want to do all that work, so it only checks it at like a couple of places, which is fine because this code has like good distance. And then to finally evaluate, we take the second part of the expanded tensor and we inner product that with U prime prime. And if you like look at the details, you'll see that that actually turns out to be the evaluation of f of r exactly as we specified it earlier. You know, you're doing all of the Lagrange coefficients with their appropriate like Lagrange basis polynomials here. Like these are evaluations of Lagrange basis polynomials, and so are these. That might not be easy to see when I do it like way too fast. But yeah, this is like the breakdown polynomial commitment scheme. And then to say a thing, like the first thing that we tried to do is like, what happens if you just like pack 16 of these guys together and try and apply breakdown? First of all, you can't like, suppose your encoding scheme here is like Reed-Solomon. Your Reed-Solomon alphabet needs to be large enough. So you need to pretend like each of your symbols when you're encoding is at least like f2 to the 16. What if you're trying to commit to like a bunch of f2 elements? Well, you don't want to blow one bit into 16-bit and then do the encoding because that's like a 16x overhead that you'd like to avoid. What you can do instead is you can try packing them first into like 16-bit elements and then doing that encoding. Long story short, that does not work either. And you need to, in fact, use or like Reed-Solomon codes, like the extension code of a Reed-Solomon code over this like weird tower algebra, which I like realize now there's 0% chance I can explain in like a couple minutes. But the upshot is that, you know, there's sort of like an interplay between two different fields and everything is like chosen very, very carefully to make breakdown still work when you're committing to only bits. Yeah, I'm not gonna, I'm very out of time, so I'm not gonna go through this. One thing I'd like to highlight is that there's a cool theory problem that I'm like quite interested in, which is like kind of embedded in breakdown and other similar like commitment schemes. And it's this idea that like, hey, if any of these guys here are delta far from the code, then if I take a like random linear combination of these rows, then with high probability, this resulting guy is also going to be delta far from the code. It's kind of like a batching argument. And that's like a crucial component to the soundness argument for this PCS. And there's like a lot of work in that statement that's happened. And like that statement is called a proximity gap conjecture. And it turns out that like if you improve the parameter delta to be like larger, that has like a very, very, very impressive impact on the resulting proof size of the overall SNARK. So if you guys are looking for like an interesting theory problem that would directly have applications to like modern proof systems, this proximity gap like flavor of things is definitely one avenue you could consider exploring. Okay, yeah, I'm sorry that I had to rush this. Maybe this is the part you guys were most excited about, but I felt like it didn't make sense to talk about this without understanding the whole overlying system. But yeah, I mean, if any of you are interested in this kind of stuff, I'm so happy to yap your ears about it. another time. Anyways, yeah, I'll leave it there and ask if you guys have any questions.
I guess big picture, like doing all of this, it seems the biggest thing is getting the, like not having to blow up things from bits to the elements. Like what does that translate to in terms of like verification size, proof size, things like that? Is it like a best case like key fold improvement, or
It's close to optimal. So like whatever you think the number should be, it's close to that. Yeah, and there's like very little extra overhead. Like to say what you're thinking is like committing to like n bits versus n 128 bits is almost like 128x smaller
and
in
so
terms of like the proof sizes.
so
Yeah.
the proof size is the main thing you're trying to optimize here, or does it also translate to like verification time or
Proof size is the main thing that people are caring about. But it does also, of course, actually, to be honest, like there's some other like things that I maybe should have mentioned. Like the things that people care about most in your SNARK proof systems today are prover efficiency and proof size for reasons. Verifier efficiency is like not really the main thing that people truly care about. And prover efficiency is better because like when you do these opening proofs, like a lot of your arithmetic is on small fields, and we can do small field arithmetic well. But yeah, the proof sizes are actually noticeably smaller, and proof sizes here include the opening proofs, by the way. Any other questions?
Can you say briefly how to do the range check?
How to do the range check? So like first you get the like range checks for free for the columns. If you declare the column to be like a t iota column, then you've already like, because this is a multilinear polynomial commitment scheme for like a specific tower ti, right? Like the correctness of the PCS already tells you that all of the values are in the range 0 to 2 to the 2 to the I. But for other types of range checks, you'd have to do it like the normal way. Maybe use a lookup table, maybe use like specific constraints. Yeah, like it's very hard to give an overview of this whole space because what happens is once enough people start trying to hyper optimize something, things get messy conceptually, and there's just no more clean picture. But the only reason I give that disclaimer is like if you start to see something that looks maybe not congruent with what I showed you here, that doesn't necessarily mean that you're wrong.